uniform circular motion occurs when an object is moving in a circle with constant speed. Consider uniform circular motion occurring around a circle of radius r. Think of a spinning wheel centered at some point that's not the origin. Let's call this point AB. If we were moving in the counterclockwise direction and this circle were centered at the origin, then our position vector would be r of t equals capital R cosine omega ti plus capital R sine omega t j. Here the omega is moderating the speed. It's telling us the speed at which we're going around the circle. So if omega is small, we're going around the circle more slowly. And if omega is large, we're going around the circle quickly. Specifically, to understand omega, imagine if we start at this point at t equals 0. After how much time will we return to this point? Well, we'll return to this point when omega t is next to pi, because we want to take cosine of 0, that's equal to cosine of 2 pi. When is omega t 2 pi? When t is 2 pi over omega. So if omega is quite large, 2 pi over omega will be quite a short amount of time. We call this return time the period, so this circular motion has period 2 pi divided by the magnitude of omega. Of course, it also has radius capital R. This parametrization wasn't quite right. It would be the right parametrization if this uniform circular motion were centered at the origin, but we're not centered at the origin, so let's write down the correct parametrization. The fact that we've shifted the center of our circle should shift our x-coordinate by positive a, and it should shift our y-coordinate by positive b. So our correct parametrization is r of t equals a plus r cosine omega t I plus b plus r sine omega t j. This describes at time 0 the point a plus r comma b. That's right here. Now let's find the velocity and the speed of motion about this circle. To find the velocity vector, v of t is equal to dr dt at time t. And so this is the derivative of a is going to be 0. The derivative of r cosine omega t with respect to time is going to become, the r is a constant, the derivative of cosine is negative sine, the omega comes out from the chain rule, so we have negative r omega sine omega t I, and the derivative of the y-coordinate, well, the derivative of b is just 0, and of r sine omega t, we'll get plus r omega cosine omega t j. So note that the velocity vector, its magnitude and its direction, they don't depend at all on where we center the circle. Instead, at a point on a circle, they'll point in a displacement direction. For example, when we're right at 0, the velocity vector is pointing this way, and then this way, and this way, and this way. The velocity vector is always pointing tangent to the path. Now that we have the velocity vector, let's find the speed. The speed is the magnitude of the vector, and it's equal to the square root of the squares of the components. So we have r squared omega squared sine squared omega t plus r squared omega squared cosine squared omega t. This is r squared omega squared times sine squared omega t plus cosine squared omega t, all to the 1/2. Note that this is just 1, thanks to my favorite trig identity. And so we get the square root of r squared omega squared. And that's going to be r times the magnitude of omega. So this is r times the magnitude of omega. That gives our speed as we go around the circle. So as you can see, when omega is small, our speed is slow. And when omega is large, our speed is large. What about the acceleration vector? What's happening to acceleration when we move in uniform circular motion? Well, to find the acceleration, we'll take the derivative of the velocity vector. And so we have negative r omega squared cosine omega t I minus r omega squared sine omega t j. This is negative r omega squared cosine omega t I plus sine omega t j. So note the negative sign and then the cosine omega ti plus sine omega tj. Cosine omega ti, these plus sine omega tj is a vector that points directly outward from the center of the circle. And this negative sign means that the acceleration vector at a point on the circle points inward towards the center of the circle. Now it might be long or it might be short, but the direction of the acceleration must be inward towards the center of the circle, exactly towards the center of the circle. Now that's quite interesting, actually. Our velocity vectors are tangent to the circle, and those should be of the same length. And our acceleration vectors point directly inward. And this means that for uniform circular motion, at a particular time t, the acceleration at time t is perpendicular to the velocity at time t. This has physical meaning. This means that the acceleration is changing the direction of the velocity vector, but not its length. And that's exactly what's happening in uniform circular motion, where the speed is always the same. So we are accelerating because the velocity vector has length as well as direction, and the direction needs to continuously change. But its length is not changing. And a hallmark of that is the fact that these two vectors, the acceleration, which is the change in velocity, is perpendicular to the velocity. So all that's happening is the direction of the velocity is changing, while its length is not. Consider these two vectors at a particular time t. So we have a velocity vector and acceleration vector. Could this particular object be in uniform circular motion? V dot A is equal to 1 minus 2, which is negative 1 here, but we expected these two vectors to be perpendicular for uniform circular motion. So no, this object is not in uniform circular motion. What if we're told a velocity vector during uniform circular motion looks like this, and the acceleration vector looks like this? What direction are we moving around the circle? Well, we know the acceleration vector points towards the center, and that the velocity is tangent to the edge, so we can now draw the circle using that information, and so we can see that we're going around counterclockwise.